Kadota from IBS. So Kenji did his PhD at the University of California, Berkeley, and then went for several postdocs at Fermilab, Minnesota, and Michigan, and then one at Nagoya University in Japan. And since 2014, he is a faculty member at IBS in Korea, and he will tell us about 21 centimeter probes on axion dark matter from minihalos. So please, Kenji.
Thank you for a nice introduction, and thanks for the invitation. So today I'm going to talk about 21 centimeter probes on axion dark matter using so-called mini halos, small halos, based on the work in collaboration with Toyokazu Sekiguchi at KK and Hiroyuki Tashiro and Kyoto Moichiki at Nagoya. The Hayato Shimabukuro, he's now in China faculty. So let me get started what kind of model I have in my mind today. So I'm going to talk about this post-inflation peak breaking scenario. By the way, this is the conclusion of my talk today. So 21 centimeter can probe much heavier axion mass than the current CMB or Lime alpha. Okay, so now let me get started with the model. So the model I have in my mind is this axion model. So in the early stage of the universe is so hot and dense, so some symmetry which are broken at a low energy universe presumably could be restored. So there's like U1-like symmetry in the very early stage of the universe. And then that U1-like symmetry gets broken and produce the Mexican hat potential. And I'm going to particularly talk about this Mexican hat potential got produced after inflation. And what it means is this angle theta at the bottom of Mexican hat is completely random. And each Hubble patch is causally disconnected. So that if we look at a little bit later time, which has a bigger horizon patch, which can include lots of smaller patch at the early stage of the universe, can include lots of random phases. If this Mexican hat got produced during the inflation, then small patch got expanded. So our universe includes only one single theta value. But I'm going to talk about the post-inflation symmetry breaking, so that our current universe is filled with lots of randomly distributed theta values. And when instant effects occurs around QCD phase transition and 110 MeV for the case of QCD, this Mexican hat potential gets lifted. So we just Taylor expand the potential around the minimum. So let's consider m square phi square potential. And this amplitude of oscillation is proportional to theta. So axion corresponds to angular degree of freedom. And it's this axion decay constant is the size of the Mexican hat times theta. So when it got lifted up, there's oscillation, but that amplitude is proportional to theta square. And because theta is randomly distributed, it means there's a huge density fluctuation in the universe. So if you just calculate the variance, the ensemble average of the fluctuation delta defined by the fluctuation with respect to the uniform background density, this bar means the average value. Then, as you may expect, because theta is random between minus pi to pi, the fluctuation turns out to be of order unity. And if you consider Cmb Power Spectrum, which is a fluctuation in the Fourier space, then power spectrum turns out to be inversely proportional to k to the cubic power, because instead of integrating for whole K space, we have to cut off at some particular scale. We call it K oscillation scale, which corresponds to the horizon size when this oscillation starts. So when potential gets lifted up, and when the Hubble constant and axion mass becomes of comparable order, it starts oscillation. And here, there's a suppression of the spatial fluctuation due to so-called Kibble mechanism, because before oscillation starts, the Lagrangian has a spatial gradient term. So inside the horizon patch, which is causally connected, it's energetically more favorable to erase out the spatial fluctuation. So that's why we put the K cutoff, which corresponds to the horizon when oscillation starts. Once oscillation starts, there's a time derivative in Lagrangian too. So this Kibble mechanism doesn't work anymore. But before oscillation, spatial fluctuation gets erased out. So instead of integrating from 0 to k infinity, we cut off at k oscillation. K is a wave number, so large k means smaller scale. So there's a cutoff, which means there's a fluctuation on the scale outside horizon scale where there's no causal contact. So this fluctuation is completely random. It's Poisson noise, just white noise, flat noise, up to the horizon size at oscillation k cutoff. So if you just do the integration, so the k to cubic power, and because the variance is of order unity, it turned out this the perturbation due to this randomly distributed white noise leads to the flat spectrum whose amplitude is inversely proportional to k to cubic power. So this is the kind of model I have in my mind today. And I call it axion-like, not exactly axion, because for the case of axion, we know this lifting of the potential occurs around 100 MeV, but the axion-like means I completely treat mass and axion decay constants as a free parameter. But I still have this kind of model where the density fluctuation was caused due to the random distribution of the angle theta. So pictorially, the perturbation looks like y-axis is a dimensionless power spectrum. So I multiplied by k cubic power to make it dimensionless. So because this white noise is completely flat, if we multiply by k to cubic power, it has a slope of 3. And those different color represents the perturbation due to axion. We can treat axion fluctuation effectively ice curvature perturbation on top of the standard adiabatic perturbation, presumably coming from the inflation. So this black one is just a standard adiabatic perturbation in a lambda CDM. And on top of that, we have a huge fluctuations due to this random theta distribution. And in my talk today, I particularly talk about so-called minihalos. And the 20 centimeter turns out to be sensitive to the mass range of around 10 to the 4th to 10 to the 8th solar mass for the reason I'm gonna come back to later on. So depending on the cutoff corresponding to horizon size when oscillation starts, this peak of the ice curvature or ice axion perturbation changes. So from this picture, because we are interested in this kind of mini-halo mass range, which corresponds to around k of 50 to 1000, the sensible k oscillation cutoff range would be around like 10 to the 4, it's blue curve, and red line about 10 to the second or so. So 10 to 2 to 10 to 4-ish is the kind of horizon size I'm interested in because those perturbations affect the structure of the structure formation of the mini-halo range, which I'm interested in. So this is a basic starting point, okay? So today I'm going to mainly talk about this K oscillation, and later on, I translate into the axion parameter, mass of axion. And the axion mass and the K oscillation horizon when it starts oscillation is 1-to-1 correspondence. So I mainly, in the first half of my talk about the bounds on K oscillation from like 20 centimeter and translate that K oscillation into axion mass later. And it's 1-to-1 correspondence because it's the more, it's determined, horizon size is determined by the moment when axion starts oscillation. So it means if axion mass is large, then it starts oscillation earlier. So earlier means smaller horizon size. So smaller horizon size means bigger K. And if axion mass is later, oscillation starts later, so horizon size is bigger. So we can explicitly calculate a 1-to-1 correspondence. On different lines here is a model represents model dependence because some people talk about the temperature dependence of the axion mass, but if n equals 0, if it's a constant axion mass without any temperature dependence, n equals 0 corresponds to like green line. So we can make a one-to-one correspondence for axion mass and k at oscillation. And I also, sometimes when we talk about axion-like particle, people sometimes talk about this fuzzy dark matter power spectrum suppression, because for this kind of very small mass actions, some people even talk about 10 to minus 20 eV scale as a fuzzy dark matter. For such a very tiny mass dark matter to be responsible for non-negligible component of dark matter of the universe, it means separation between each particle has to be super tiny, even like 10 to minus 10 centimeter or even smaller. But if delta X is very small, from uncertain principle, delta P is big. So it means we have to treat as a wave-like nature. We cannot treat it particle anymore. And because of this so-called big quantum pressure, there's a separation of the structure. And people sometimes talk about this quantum pressure. Small delta X means big delta P. So dark matter fluctuation cannot proceed because of the big pressure, big momentum. But those scale shows up at a much smaller scale than the scale I'm going to talk about today. So those quantum pressure, which people often talk about when people talk about fuzzy dark matter, is not relevant. So I will not talk about fuzzy dark matter today. Okay, so this is just an illustration. So there's a one-to-one correspondence between axion mass and the oscillation, K oscillation. Okay, so what are the minihalos? So minihalos particularly refers to this mass range of 10 to the 4th to 10 to the 8th solar mass in my today's talk today. And the reason is I'm interested in this 21 centimeter observation, which I'm going to talk about later on. And 21 centimeter cares about neutral hydrogen, because neutral hydrogen has a spin interaction between electron and proton, so they have to be combined together. I will explain a little more detail, but 21 centimeter comes from neutral hydrogen. So if the halo mass is too big, it can host the stars inside the halo. And if there's a star, there are lots of energetic photons emitted from the stars, and those stars ionize the neutral hydrogen. So I don't like the stars. And I want to talk about starless halo. Halo which is small enough so that it cannot host the stars. And the neutral hydrogen can stay neutral. And I also don't want to talk about too small halos because it becomes below baryon Jeans mass scale. The baryon fluctuation cannot catch up with the dark matter fluctuation. So lower bound comes from the baryon Jeans mass, because the baryon has a finite thermal velocity dispersion. Dark matter baryon fluctuation is suppressed below this baryon Jeans mass scale. So lower mass coming from this baryon Jeans scale, and upper bound coming from the fact that the halo cannot host the stars anymore. Okay, so pictorially, in the early stage of the universe, like 0, 30, or even 20 or something, when halos getting started formed, there's a lot of small halos. So blue one represents small halo, which is cold and they cannot form the stars. But if we wait long enough, say 15 or so, there are bigger halos as well. In the bigger halos, as I said, energetic photons emitted from the stars can ionize the neutral hydrogen. So this white region represents the ionized regions. And if we wait long enough, more and more regions are ionized. And I want to discuss the 21 centimeters coming from this neutral hydrogen in this small halo, small mini halos. And because it's so small, it's dense and compact, filled with neutral hydrogen. So this is what I mean by mini halos, 10 to the 4th to 10 to the 8th solar mass. And that the fiducial redshift I'm going to talk about today is around redshift of 10. The observation becomes harder if we try to look at the higher redshift. So it's easier to see smaller redshift because it's closer to us. But if we look at the too small redshift like 9 or 8 or 7, lots of ionization already got started. So gas physics become too complicated. Lots of energetic photon from the stars and early forming galaxies. So 10 is sort of the fiducial redshift before gas physics become too complicated and still close enough to our current universe. Okay, so coming back to that power spectrum plot again. So the scale I'm interested in is around 10 to 4th to 10 to 8th solar mass. So in terms of wave number, it's about 50 to 1,000. So this is much smaller scale than Cmb, or galaxy clusters, or galaxies. Sometimes many people talk about very small mini-halos whose mass can even go down to like 10 to minus 10 solar mass. So those are also mini-halos, very small mini-halos. Those very small mini-halos are not what I'm going to talk about today, because they are too small to be observed by 20 centimeter. So today I'm going to more talk about the relatively large mini-halos. Okay, so this is the scale I'm interested in today. Okay. By the way, if there are any questions, please feel free to interrupt me anytime. Okay. So, I'm going to talk about how this random distribution of the angle theta can affect the abundance of the mini-halo and epoch of the mini-halo formation. So coming back to this enhancement of the matter power spectrum again, this cutoff is determined by K oscillation cutoff. And this is the left-hand picture is the picture for a fixed K oscillation. So K oscillation determines the amplitude and also determines where the cutoff shows up. So K 10 to the 4th corresponds to this blue one, okay? And this guy should affect the scale about K to like 1,000 or so. Okay, so in the standard lambda CDM, there's essentially no mini-halo formation around the redshift of 100 because it's too early epoch. But if there's small fluctuation at such a high K, there's already lots of mini-halos formed. So y-axis represents the number density of the halos, and the x-axis is the mass of the halo. So at a redshift of 100, this blue one represents the mini-halo in existence of this axion curvature perturbation, which gives additional power at a small scale. If there's no axion, the abundance is too small to be shown in this figure. So there's no solid blue one, no axion case because it's a small abundance. And if we wait until redshift of 10-ish, this blue one in axion scenario shifts to this red dotted line. So we are dealing with the hierarchical structure formation. So this blue one, this very small one, gets assembled to form the bigger halo in hierarchical structure. So small halo abundance gets reduced a little bit, and then goes as to the abundance of the little bit bigger halo. So that's why the transition from blue one to red one, there's a small decrease in the lower ends, and the higher ends get increased. And also, if we wait long enough, there's enough time for the bigger halo to be formed too. So there are more and more bigger halos later on. And around redshift of 10-ish, even for the non-axion scenario, we start seeing some halo abundance here. But for the small mass region, the abundance is much, much bigger for the axion case. Dotted red one is much bigger than no axion case, solid red. Even though for the big scale, like 10 to 10 solar mass is around galaxy scale, around this scale, standard adiabatic perturbation start becoming dominant. So there's not so much difference between the axion and no axion scenario anymore. Because at the large scale, small k, this black adiabatic perturbation dominate anyway. And it is good because it does not affect the like Cmb or lime alpha, for which we have a very good precise data. So I'm interested in scenario where so large scale structure do not get affected so much, but only small scale structure get affected quite a lot. So at the rate shift of 0, there's not so much difference anymore because structure formation already got started enough. And more in the bigger mass range, this standard adiabatic perturbation dominates anyway. Okay, so this figure illustrates how the epoch of the small mini-halo formation got affected due to the additional power at high K. So let's look at this fiducial rate shift of 10, and let's see how this axion ice curvature perturbation affects the abundance of the mini-halos. So if we choose cutoff of like 10 to the 5th, then because power of the axion ice curvature perturbation is inversely proportional to K to the cubic power, so 10 to the 5th is quite a large number. So ice curvature perturbation is quite small, amplitude is small. So there's not so big difference between this adiabatic no action case, black curve, and this pink one. But if K becomes a little bit smaller, like 10 to the 4th, then we start seeing a big difference between black and blue. But if you go to even smaller one, like green one, for instance, it's good that the amplitude of the ice curvature perturbation, axion ice curvature perturbation gets big. But if ice curvature perturbation is too big, very big, then those mini halos got formed too early. So if we wait until rate shift of 10-ish or so, those small halos got assembled to form the larger halo, which 20 centimeter cannot probe anymore because big halos can host the stars. So there's some optimal K range, which is not too big or not too small. And it turned out the optimal K range is around 10 to the 4th. So if you go to as small as K of 10 to seconds, you see this is red one with action scenario, and the black one is no action scenario. So red one produced small halo too much at a too early stage. So most of them already got assembled together to form the big halos around the rate shift of 10. That's why there's a big suppression at a small mass range and a big enhancement for the heavier halos. Okay, so this is how this axion perturbation can affect the formation of the mini halos. Okay, so we can see by eyes how they get affected. So how do we see mini halos? So the way the probe I want to talk about is 20 centimeter. So 20 centimeter is just this wavelength which is emitted or absorbed by this hyperfine splitting. So this is neutral hydrogen. So there's a spin parallel and a spin anti-parallel. So there's this energy split is just very, very tiny, like micro EV. So in terms of wavelength, it's 20 centimeter and it's gigahertz. So it's exactly radio frequency range. So we can see it from radio telescope. And because the neutral hydrogen is the most abundant element of the universe, so if we can see the distribution of the neutral hydrogen in the universe, we can presumably infer the underlying dark matter properties because those neutral hydrogen presumably follow the distribution of the dark matter. And this 20 centimeter is quite common, for instance, to study galaxies. So this is a rotation curve of the galaxies. So toward the center of the halo galaxy, there are lots of stars. So we can measure how fast the galaxy is rotating from Doppler shift of the stars. But if we go a little further from the center of the galaxies, there's no visible objects anymore. But we can still measure the rotation speed by looking at the emitted photon from neutral hydrogen. So rotation curve data coming from 20 centimeter observation for toward the higher radius from the center. So this is a famous rotation curve plot, which indicates the existence of the dark matter. And so there are already 20 centimeter observation in a local galaxies or local space in a current universe from the like galaxy or galaxy clusters, because there are lots of neutral hydrogen locally. But I'm more interested in the large scale structure of the universe through 20 centimeter. So 20 centimeter signal of the current universe is 0 because the universe is ionized. I need a neutral hydrogen because it's an interaction between the spin of proton and electron. So to see the 20 centimeter, we just need to go to higher redshift where universe is still neutral. So redshift above 6 is the high redshift I'm interested in. Okay, so when I say 20 centimeter, I'm talking about a signal from the universe which is still neutral or partially neutral if it's during the reionization epoch. Is it clear? Yeah, so I'm going to talk about a high redshift because there are a lot of universes still not completely ionized yet. So how do we see the minihalos? How do we see the minihalos? Because it's a 1 gigahertz radio telescope, radio frequency, we can use a radio telescope. But it's good because it's only visible wavelengths and radio frequency photon, which can reach the Earth. All the other frequency photon is blocked by the atmosphere. So we need a satellite. But for radio observation, we can do it on the Earth. And for the sensitivity estimation later on in my talk today, I'm going to talk the sensitivity corresponding to SK-like experiments. And Australia is a key player of the SK. And Australia's SK covers a little bit lower frequency range, and South Africa is a big dish telescope, covers a little bit higher frequency range. We cannot cover such a wide range of frequency by only one experiment. So they split the lower frequency part and higher frequency part. And this is the picture of the big data agreement between SK and LHC. So it's not a problem, but the interesting science is a big data science. So for LHC, last 10 years of running, they saved around 300 petabytes of data in the hard drive. SK eventually is supposed to deal with like 300 petabytes of data every single year. So we expect huge data coming in, and we can do lots of precision cosmology science out of this kind of big telescope like SK. So it's promising. Even the still future, I had a construction to start this year. So we will see how it goes. But I'm going to talk about the sensitivity expected for the SK-like experiments today. So just to show you more impression how cool this 20 centimeter observation would be, let me show you this Cmb Power Spectrum. So probably you're familiar with this Cmb Power Spectrum oscillation. And the Cmb Power Spectrum gets suppression due to so-called silk damping when it goes to scale K 0.1 means about 10 megaparsec, because last scattering surface is not instantaneous, it has around 10 megaparsec thickness. So if you go to K 0.1 or so, we have to worry about the diffusion of the CMB photons within finite thickness of the last scattering surface. So there's a diffusion damping here. So this is the highest K CMB can probe. But compared with CMB, 20 centimeter can probe much higher K. So it means we can get a much better angular resolution. 20 centimeter also has a limitation because if we go to such a high resolution, we have to worry about the thermal motion of the gas. So this spectrum gets Doppler broadened. So the thermal motion puts up the limits, but it's much smaller scale than CMB. So if you just count the number of Fourier modes available compared with CMB, CMB is just one-dimensional snapshot of the universe at the last scattering surface. And while 20 centimeter gives three-dimensional tomographic view of the universe because we know it's 20 centimeter at rest. And what we are going to observe is a red-shifted 21 centimeter signal. So we can get a three-dimensional picture snapshots of the universe with a much, much better resolution. So the number of Fourier modes available is for the case of the CMB, in terms of L, we can go to like 2,500 or so and squared. But for 21 centimeter, the 2,500 times like factor 10 to the fourth and the cubic power. So if you just do simple math for the statistical error, which is inversely proportional to number of Fourier modes available, we can guess that we can do a very precise cosmology using 21 centimeter. So in the same way, CMB could revolutionize the precision cosmology. 21 centimeter can well revolutionize the precision cosmology in the future. Okay, so this is just the advertisement of the how good, how cool 21 centimeter observation could be. Okay, so what actually we measure in the actual experiment is so-called brightness temperature. So the picture looks like following. So we prepare some flashlights. Let's use Cmb photons as flashlight. And the Cmb photon goes through the neutral hydrogen gas clouds with the optical depth tau. So what we measure is so-called brightness temperature. So Cmb photon gets suppressed by the factor E to minus tau. And Ts is called spin temperature in 20 centimeter literature, but it's just in a nuclear physics textbook, it's an excitation temperature. So it represents the abundance ratio with the spin triplet and spin singlet state of the neutral hydrogen. And this is just excitation temperature, but 20 centimeter people call it spin temperature. So there's a neutral hydrogen gas cloud, which has a spin temperature Ts and the optical depth tau. So what we're gonna get is that this brightness temperature, so spin temperature is suppressed by E2 minus tau, and the Cmb temperature is also suppressed by E2 minus tau. And what we're gonna measure is this so-called brightness temperature with respect to the background temperature, which is Cmb. So what we measure is so-called this differential brightness temperature. So brightness temperature with respect to Cmb background. So as you expect, if tau thickness is big, it means there's a very dense neutral hydrogen, so signal is bigger. And if the spin temperature, Cmb temperature is more different, then signal is bigger. Okay, so you look at this Cmb black body background spectrum, and if there's some increment, it means this spin temperature was bigger than Cmb temperature. So we see increase and decrease with respect to the Cmb spectrum. And that's the way we can see this effect of the transition in a triplet state and singlet state of neutral hydrogen. So we're going to measure this so-called differential brightness temperature. Okay. So this is what we measure in an experiment. And so again, pictorially, so lots of Cmb photons coming from everywhere. And at a high redshift universe, there are lots of diffuse neutral hydrogen everywhere. But on top of that, there's a mini-halos. And mini-halos includes lots of neutral hydrogen inside it. And those Cmb photons go through on top of those diffuse neutral hydrogen. It also goes through very dense neutral hydrogen clouds. So compared with lambda CDM case, we expect more abundant mini-halos in axion scenario. So 20 centimeter signal should differentiate among different axion parameters compared with lambda CDM with no axion. So this is a big picture. Okay. So the actual observation we expect is this mini-halos, spatial distribution of the mini-halos presumably follow the underlying dark matter distribution. So this 20 centimeter signal should be proportional to underlying dark matter spatial distribution. But we usually have this so-called bias factor because this following underlying dark matter spatial distribution is not perfect. So if exactly follows with each other, bias is 1, but usually there's some bias factor. So usually we have a slight difference from underlying dark matter distribution, which is represented by this so-called bias factor. And this delta TB includes the effects of the abundance of the mini-halos, for instance. So if there are lots of matter per spectrum enhancement, it means more mini-halos. So the final differential brightness temperature observation should be bigger if there's a lots of more abundant mini-halos. So the bias factor, for instance, is represented by this red curve here. So as a function of z, this dotted one is a no action case, and the solid one is with action. And bias should be small in action scenario compared with no action scenario because mini-halo is more abundant in action scenario. So it means that in a lambda CDM, mini-halos are very rare objects. So it's more biased to the density fluctuation. If suppose there's only one mini-halo, then this one mini-halo should be in the most likely in the highest peak of the underlying dark matter density fluctuation. But if there are like thousands of mini-halos, probably mini-halo is more distributed. So rare objects tend to be biased more to the fluctuation of the underlying dark matter. So it's reasonable that we expect a mini-halo which are rarer in lambda CDM should have a bigger bias, more bias toward the density fluctuation than the action scenario. But this difference of the bias is totally overcome by this number density abundance, because abundance of mini-halo in action scenario is bigger. So the final 20 centimeter signal should be much bigger in the action scenario. So this black one represents this delta TP factor, and the dotted one is much smaller in a no action scenario. That's a function of z. This brightness, the signal gets bigger and bigger because if we wait more, the more halo production. So it's going to increase. So underlying dark matter spatial fluctuation times bias times factor which has an abundance of mini-halos is what we observe. So if we plot the correlation, 2-point correlation, we expect the shape should be pretty much same as the dark matter correlation function. So those different lines represent the correlation between different redshift bins. But let's forget about binning of the redshift. So let's talk about only this black curve, which is an autocorrelation between the redshift 10 bins. So inside the same redshift, we calculate a 2-point correlation function. And the shape is pretty similar to just the matter power spectrum, standard dark matter power spectrum shape. But the amplitude is different in action scenario. So black solid is the action correlation power spectrum. And this dotted one is lambda CDM. And the reason why we have a bigger signal is because we have more neutral hydrogen thanks to more abundant mini-halos. And the mini-halos got produced earlier when universe has denser, means that those mini-halos are more denser and more compact. So there are lots of neutral hydrogen inside mini-halos. So this is just to show you how much enhancement we can expect in a 20 centimeter signal, thanks to lots of abundant mini-halos packed with neutral hydrogen. Okay? Yeah. So we did a simple likelihood analysis to see how precisely we can measure this cutoff K, because if we change this cutoff K, that's ice curvature perturbation shape changes. And we found that if K oscillation is too big, then amplitude of this axion ice curvature perturbation is inversely proportional to K to cubic power. So amplitude is too small, so we cannot see the enhancement so much. So we found as long as K is below 10 to the fifth, we can measure this K oscillation, estimate the K oscillation with a reasonable error bar. So with respect to the amplitude of K oscillation, error itself is smaller than the K oscillation. So if we just in this one-to-one correspondence plot of axion mass and K oscillation, this 20 centimeter signal experiment is sensitive to the parameter range where K is below 10 to the 5. So below this black solid line. So if we consider the constant axion mass without temperature dependence, so n equals 0 is at this purple line. So it means 20 centimeter can prove axion mass up to around here, 10 to the minus 13. So that's why we put a bound of 10 to the minus 13. So if we do not see the effect of this enhanced minihalos, it means axion mass has to be bigger than 10 to the minus 13 eV. And this is much heavier mass, which other observation like Lyman alpha or Cmb cannot prove. So that's huge improvement in the sensitivity of the axion mass. Okay, so this is just the illustration of how future 20 centimeter would be powerful to prove the axion mass range. Okay, great. So this is the case where we use the Cmb background as a flashlight. And 20 centimeter is hard measurement because of the lots of foregrounds. So this is the picture of the foreground. So flashlight of Cmb photon is Cmb is 3 Kelvin. We are trying to measure the increase or decrease of the black body Cmb spectrum of order like 10 millikelvin. So huge 3 Kelvin background flashlight is a very tiny of order 10 millikelvin. And on top of that, there are lots of foreground, extragalactic foreground, galactic foregrounds of order like Kelvin or 10 Kelvin-ish. So it's very hard measurement. So and just to show you even more figures. So this is the figures of the power spectrum. So Cmb power spectrum, 20 centimeter power spectrum. So this is an anisotropy. So for anisotropy fluctuation power spectrum, 20 centimeter signal is much bigger than Cmb power spectrum because Cmb power spectrum is delta T over T is 10 to minus 5. So 20 centimeter is much bigger. So it looks good because amplitude is much bigger than Cmb anisotropy. But again, the problem is the foreground because as we look at a very low frequency range. So this is a frequency of the Cmb experiments of like 100 gigahertz or 10 gigahertz. But the radio telescope goes even down to like 1 gigahertz. So this orange one, synchrotron radiation, totally dominates. So this galactic synchrotron radiation totally dominates. So one of the hard things in a 20 centimeter experiment is to deal with this big foregrounds. But I hope it's like very sensitive experiment like SK can deal with this. But currently, we still have not measured the 20 centimeter signal with enough confidence partly because of this huge foreground. Okay, so one thing we could do is why don't we use other flashlight, not like Cmb? The problem of Cmb is it's a diffuse signal. So Cmb comes from everywhere. And the foregrounds, galactic foreground synchrotron radiation is also diffuse coming from everywhere. So instead of looking at this diffuse signal, how about looking at a point source, which is very, very bright. So one possibility is to use a very bright quasar which emits lots of radio photons. So this is called 21 centimeter forest. So the picture is similar to CMB case. So instead of CMB, like diffuse signal, we just look at one very bright point source. And this radio photon emitted from this bright source goes through this dense cloud of neutral hydrogen. So if you measure flux, so there's of course absorption due to the diffuse sea of neutral hydrogen, because we are looking at a high redshift universe as still neutral. So there are lots of neutral hydrogen, but in the sea of neutral hydrogen, there are lots of dense compact mini-halos. So once those photons go through dense clouds, mini-halo, which is packed of neutral hydrogen, there's a deeper absorption. And in an actual simulation, it actually looks like a forest. So this uniform decrease of the flux due to the sea of neutral hydrogen, but on top of that, whenever it passes through the mini-halos, there's a deep absorption lines. So this looks like a forest. So we call it 21 centimeter forest. So if we, in a lambda CDM without axion, if we find like only 3 deep absorption lines, but in the axion scenario, we may have like 20 absorption lines. So by counting those deep absorption lines, we can distinguish from like axion scenarios and lambda CDM without axion by the difference in the abundance of these deep absorption lines. Okay, so this forest looks different. Okay, so let's apply our similar formalism for the 21 centimeter forest too. So we have some additional power from this axion fluctuation due to random theta phase distribution. And if those fluctuations affect the relevant mass range of the mini-halo, like 10 to the 4th to 10 to the 8th solar mass, it can change the abundance of mini-halo, so it can change the abundance of the deep absorption lines. So this y-axis represents the expected number of absorption lines as a function of the optical depth, how dense that mini-halo would be. So this black one is no axion, so we can expect of order like 10 absorption lines if we just keep looking at the very bright source, like quasar at a high redshift. But if we add some axion ice capture perturbation, if it's like 10 to the 5th, then amplitude is small because 1 over k to cubic power. So we don't see so much difference, but like 10 to the 4th or 10 to even 3, this amplitude of the axion ice capture fluctuation gets bigger and bigger. So we see bigger difference in number of these absorption lines. But as I said, if the K oscillation, this horizon size when axion starts oscillation gets too small, then means that too big power is added at a small scale due to axion ice capture perturbation. So those mini-halos formed too early. So if we wait until redshift of 10, those mini-halos already got assembled to form the very big halos. So those are too big to see by 20 centimeter. It's out of range of the mini-halos I'm talking about today. So there are some optical K range, which turns out to be around 2 times 10 to the 4. There's a minimum K and maximum K. So this blue region represents the parameter space, which is sensitive to 20 centimeter forest observation. So again, looking at this mass independent axion mass case and equal 0 case, we can probe between 10 to the minus 17 up to around 10 to minus 12. But for the lower range, like 10 to minus 17, Lime alpha already can probe. So it's a big complementarity between Lime alpha and 21 centimeter, because up to 10 to minus 17, Lime alpha can probe, and above 10 to minus 17, 21 centimeter can probe. So if we do not see any signal or any difference from lambda CDM in the future, even with 20 centimeter experiments, it means axion mass has to be bigger than 10 to minus 12 CV. So this is another application, the radio telescope like SKA, to prove the axion scenarios, in this case, using 20 centimeter forest. So this is good because this is essentially foreground free. We are looking at a very, very bright source. So this diffuse foreground is negligible. The caveat here, though, is we may not have such a bright source at such a high rate to begin with. And we still have not found such a very bright radio loud quasar at a high rate shift above 6. But there's a good candidate now. So radio loudness is defined as the ratio of the flux in the optical band, optical frequency, and the flux in the radio frequency, because quasar emits lots of photons with different frequency range, and radio loudness is defined by the ratio between optical band and radio band. And those gray region is called radio quiet, and the white one is radio loud. And we recently found a good candidate, which is very, very radio loud, this red one. And it is expected to be located at like latest 5.8 or so, latest of 6 or so. So there are still enough neutral hydrogen. So people are now doing the follow-up survey to measure the more precise rate shift. And they also want to make sure such a bright source radio loud quasar is surrounded by the dense gas so that there's enough absorption due to neutral hydrogen. But if it turns out to be really radio loud, surrounded by big dense clouds, we may be able to see the 21 centimeter forest. And this is bright enough so that the flux is over the 10 millijansky, which is the sensitivity of the SKA. Okay, so this is another application of 20 centimeter experiment like SKA, and using the very bright source. Okay, yeah, so let me wrap it up. So I discussed the this post-inflation PQ symmetry breaking scenario where this angle theta is distributed randomly. So it just gives a white noise, Poisson noise, and it gives a big perturbation at the small scale. And it can change the abundance and formation epoch of the minihalos. The minihalos are packed with neutral hydrogen so that we can see the those effects of neutral hydrogen through 20 centimeter experiment like SKA. And we can expect much tighter bounds on axion mass, even though we have to take it with a grain of salt because CMB and Lime alpha are using the currently available data. And I'm talking about the future expectations. So it's a little bit unfair to compare those bounds, but I think it at least can give some prospects for how precise physics, what kind of physics we can do using 20 centimeter in the future. Yeah, that's it.
Yeah. Thank you very much, Kenji, for a very clear and interesting talk. So we have time for questions. Who wants to start?
Can I ask, I'm sorry if I missed this, if you did mention this, but am I right in thinking that you are not considering any topological defects which could be produced after the Peccei breaking?
Yeah, right. So I did not consider topological defects, but it's an important issue because when we estimate the axion abundance, we need to know how much dark matter, axion dark matter coming from a cosmic string, for instance. Yeah. So I did not discuss the those topological defects. I assumed the 100% dark matter coming from this oscillating axion field.
Do you know what the kind of effect of that would be on the minihalos?
So for instance, So for instance, when I relate this K oscillation, this one-to-one correspondence here, one-to-one correspondence is affected because when I translate K and MA, so I need to assume what's the value of the FA. So what I'm saying is I treat the FA as a free parameter, right? Mm-hmm. And I considered all the mass coming from M square, A square term. I assume this is 100% dark matter. Mm. But if you consider topological defects, actual density is this potential plus cosmic string, for instance, right? Mm. Right? Yeah. So when I translate between that K cutoff and MA, I'm assuming that this value of FA, so this rho A has FA in it. And so what I'm saying is this, when I translate between MA and K, I have to assume how much percent of the energy coming from this potential. Mm-hmm. So if I put in like topological defect, like string contribution, this effect gets smaller, right? Because some density coming from other component of the universe.
But the constraint on K oscillation, that remains the same. Is that correct? So it's only the translation, the last step.
No, because this density contribution coming from here is a proportion. So this one, 1/k oscillation times omega A over omega dark matter squared. And that omega A coming from the oscillation is I'm assuming omega A oscillation over omega dark matter is 1 is what I'm assuming now. So if 90% coming from topological defect like a string, and only 10% is coming from this oscillating that potential M square, MA square, A square, then I have to multiply the amplitude of the ice sculpture perturbation by 0.1 squared. Because this fluctuation is due to this potential. And it's
okay.
Yeah.
So it's like if axions wouldn't be all of dark matter.
Yeah, correct. So usually, our paper also discussed the case where the energy component of the so this potential, this misalignment mechanism contributes only 10% of the dark matter, for instance, instead of 100% of dark matter, which I discussed today. And the bound actually was so instead of this K of like 10 to 5, if we only 10% comes from misalignment mechanism, this black curve goes to like around here, between 10 to 3 and 10 to 4. So instead of getting the bound of 10 to minus 13 EV, the bound gets weakened to like 10 to minus 16 or so. Yeah, so in this sense, the bound gets worse. Instead of 10 to minus 13 EV, 10 to minus 16 EV. And the reason is this ice curvature perturbation amplitude gets smaller.
Okay. But whatever you basically derived for K oscillation, you could basically just, so the only place where it enters the strings or the topological defects comes in the translation here, where it's...
Yeah, sure. Yeah, correct. Yeah, because experiment, radio telescope doesn't know where it came from. Yeah. Radio telescope is just measure the K oscillation, sensitivity on the K oscillation. So theoretical interpretation is something which is affected by existence of the topological effects.
Yeah,
correct.
Okay, thanks. Other questions? Can I ask one? So you mentioned also those CMB bounds and Lyman alpha bounds, which we see here on your slide. Will they change, or that's the best possible bound one can derive?
So this change mainly coming from what's the highest K-scale. So because I'm talking about this one-to-one correspondence, if I want to change this value of MA 10 to minus 17 to like 10 to minus 15 or 10 to minus 16, it means I have to change the sensitivity of the K oscillation. So it means lime alpha has to go to even higher K if I want to improve this number. But the lime alpha is pretty much bounded by K of 10 because the lime alpha also cares about the neutral hydrogen. So it's the thermal motion of the neutral hydrogen for the lime alpha transition. And it's around 20 kilometers per second or something. So this Doppler broadening limits the lime alpha to be K of 10 or so. So I don't think it's gonna improve that much. Yeah, because it cannot go to very higher K anymore.
Yeah. Okay, so it's really limited there, and you with but with
So
you can go
I don't think it's gonna improve that much. Actually, one of my colleagues was joking that the lime alpha involves lots of gas physics. So if you know even more detailed gas physics from the more detailed simulation, error bar gets bigger. So lime alpha bounds may worse and worse. So it depends on how much gas physics we can control.
Yeah.
Okay.
Can I ask one more, or maybe I should first ask whether anyone else has a question? Just unmute yourself, or well, if not, then I wanted to ask you one more thing. So you mentioned there for the quasars that you want a radio loud quasar. So you don't want as much emission for in photons or in kind of in visible light, or is it just that you? So my question is basically: is the ratio important between kind of the radio frequency over the visible light, or is it just important that you have that large radio signal?
I think it's large. Okay, so you're saying if there's no visible photon at all, but it emits only radio photon, that may be fine too. Yeah, that's true as long as we are using only radio telescope. But what people usually do, for instance, for this P35215 case, they usually found it by optical telescope first. And then after finding this object, we do follow-up survey by radio telescope. So it's good to be able to be measured by multiple frequency. Okay, yeah, no, that makes sense. Right. But as you said, if we only care about radio telescope, radio telescope cannot see the optical frequency anyway, so only radio is fine. But usually optical telescope is easier. Right.
Yeah, thanks. Yeah. If there are no more questions at the moment, then I would say we thank Kenji again for a very nice talk, and we can stop